Hi there. Today we're going to talk about how to do a hypothesis test for the mean. And we're going to start out by talking about what the setup is. When do I do this? All right, so we always start, there's some population I want to know something about. And when we did a confidence interval, we wanted to know, well, what is the mean? All right, so we would do a confidence interval. So what do? We take a sample. And in the sample, we would have some summary statistics that we would use to come up with a confidence interval. So we'd have the sample size, the sample mean, and the sample standard deviation. And we would use this sample mean, this y bar, as an estimate of mu plus or minus a margin of error. Well, with a hypothesis test, this is like a yes or no question. So basically, what we want to know about the mean is, does it meet some criteria? All right, so is the population mean, is it bigger than some value? Is it less than some value? Or is it not equal to some value? This value we're going to call mu 0. So, is the average height less than 6 foot? This might be the 6 foot, right? So that's what we're going to do. So now, instead of just saying, well, what is mu with some margin of error, we want to know if it meets some qualification. So maybe in the past, the average height for men was 5'10", and we want to know, is the average height taller or less than that now? Okay. So let's start with an example. And so we have the wind turbine. We're thinking about investing in a wind turbine. But according to the manufacturer, in order for it to be worth the investment, your average annual wind speed should be at least 8 miles per hour. All right. So we want the average, by the way, the annual average wind speed, this is mu. This is the underlying mean for your site. Here's my site. On average, what's the wind speed there? All right. What I need mu to be over 8 in order to be worth investing in a wind turbine. So it's not so much what is the wind speed. So that would be something I would do a confidence interval for. But is it bigger than 8 miles per hour? All right. Okay, so they take a sample. A site was being monitored for a year, and for every 6 hours, the speed was recorded. And so they came up with 1,460 measurements, and on average, it was a little bit over 8 miles per hour with the standard deviation of 3.813. So we want to know, is this high enough? Is 8.029 high enough above 8 that I feel pretty sure that it's at least 8? And that is when we do a hypothesis test. All right, so my hypotheses are, we did this before with proportions, now we're doing it with means. The same thing is going to be true here. I'm going to have a null hypothesis, which I call H0. And this is going to be some equality, all right? And then I'm going to have an alternate hypothesis, and this is going to be some inequality. So the parameter, the population parameter that we're interested in here is mu. So we're going to have mu equals some value, and mu, this is going to be, here we're going to have, less than, greater than, or not equal to some value, all right? So this, the null and the alternate hypothesis are both statements about the population. What does the population look like? And one of them is true, or one is true and the other is false. So these are theories. We don't know for sure, all right? So our alternate, the alternate comes from the research question. So we look and say, well, what is it we're trying to prove here? And that becomes my alternate hypothesis, the inequality. less than, greater than, not equal. So we have here, we need it to be at least 8 miles per hour. So this is greater than 8. So that came right from our research question. And my research question here is, does this data prove that we have at least 8 miles per hour wind speed on average? Okay. So the mu over here, this is mu equals 8. So this is my null hypothesis. This is my alternate hypothesis. And when we pick our hypothesis and we have this less than, greater than, or not equal to, if it's a less than or greater than is chosen, that's called a one-sided test. So this is a one-sided test. All right. So we're only going to conclude that the mean is greater than 8 if my sample mean is high enough. If my sample mean was below 8, then that would not prove that the mean is above 8. So this is a one-sided test. All right, so let's look at our conditions. And the conditions for this are the same as for the confidence interval. And the first condition for all of my confidence intervals in tests is the independence or randomization condition. And the point of this condition, what I need is independent observations that I believe represent the population. All right, the population here is all years, it's all times, all right, because in our sample that we have, this is so weird, why is it doing that? Okay, all right. So my sample here is is monitored for a year. All right, so it's all right. So we have every 6 hours for a year, we measure the wind speed. All right. So I gotta ask myself, is that year's worth of wind speed, is that a good representation of the wind speed at this site? And I would say yes. I mean, we're getting every single day of the year, 6 hours a day. By the way, do you remember what kind of sample this is? It's not a random sample, but it's close. It's somewhat random, but it's not, we usually don't call that a random sample. This is called a systematic sample, which are excellent samples. Another example of a systematic sample is as if I survey every 10th customer or something like that. So this is a very good sample. So I think that it is that this sample should be representative, and are the wind speeds independent of each other? So if it was windy at 9 a.m., then 6 hours later at 3 p.m., is that wind independent? Maybe not, but it's going to be close enough. We're gonna take it. We're gonna say, yeah, it's definitely representative. Whether or not these are independent of each other when they're 6 hours apart, so maybe not. That's okay. All right, so let's look at the mechanics. So basically, when we meet our conditions, oh, I forgot the size. So my size condition is based on the histogram. Let me get myself some more room here. All right. So So it's based on the histogram. So with quantitative data, if we want to know if the mean is normal or not, we learned that as the sample size gets bigger, that the mean gets more normal and less variable as the sample size gets bigger. All right, so then how big does the sample size have to be for the mean to get normal? Well, it depends on what the original distribution looks like. If the original distribution is symmetric and close to normality to begin with, it doesn't take a very big sample size to get normal. If the distribution is pretty skewed, it might take a bigger sample size to get it to look normal. Because remember, normal is unimodal symmetric, this little bell-shaped guy. So it's the same on the left and the right. So if I've got data that's pretty skewed, I might need a bigger sample. So let's look. And so in order to know what the distribution of wind speed looks like, I just look at this histogram. This is my best guess at what the distribution looks like, what the actual population distribution is. So this is a pretty smooth curve. It's not exactly normal because it's not flat, you know. Normal is like, you know, would be something like this. All right, but it's close. So it's maybe slightly skewed right. So it's unimodal, slightly skewed right. All right. So, but the sample size is huge. My sample size is 1,460. All right, so for a big sample, and a big sample we said is anything over 40. All right, so if it's bigger than 40, then we meet the condition as long as as the histogram is not extremely skewed. And also it can't have extreme outliers. Now look at this, it's slightly skewed, no outliers, all right? So I'm going to say that is not extremely skewed. My histogram here is not extremely skewed, and it doesn't have any extreme outliers. So we meet the size condition. So we meet both conditions with the sample. All right, so let's do our mechanics. All right, so if it's normal, all right, so we meet these conditions, that means that my sample mean, which is y bar, the sample's big enough that my sample mean is now normal with mean mu, which is the population mean that I don't know, and standard deviation sigma over the square root of n, which I don't know mu or sigma, right? So these are unknown. I don't know what those are, but if I knew them, then my sample mean would be centered at this mu, and its standard deviation would be this, all right? So if I could calculate a z-score by taking a specific y bar, and I could subtract the mean and divide by the standard deviation. And this guy is actually going to be standard normal. This is going to be normal 0, 1, which is standard normal. So z-scores, that's why we look them up in the standard normal table, because these, if things are normal, are standard normal, all right? Well, here's the problem. I don't know what sigma is. So I have the same problem I had with the confidence interval. I don't know sigma, but I do have S. All right. So when I take my sample, I get the sample size, the sample mean, and the sample standard deviation. So I have S, and actually here it says the standard. This is S. So S, this 3.813 miles per hour, is well, especially as big as it is, that's a pretty good guess at what sigma is. All right. So what I'm going to do is I'll just use S here. All right. But when I replace sigma with S, I no longer have a Z, I have a T. All right. So my test statistic, this is T, it's not quite this, we're almost done. All right, but I'm going to take this sigma, replace with an S, and I divide by the square root. And you might have noticed I stuck this little 0 in here too. All right, and that mu0 tells me that I need to go to H0 to get this value. All right, so my test statistics, every test statistic is a calculation that assumes the null hypothesis is true. And so the question, when we get to our p-value, the question is, if the mean was 8, all right, if for this particular one, if the mean wind speed was 8 at this location, is it unusual to get a wind speed of 8.029, which is what I actually got? So here's my theory, right? Mu equals 8. Here's what happened. Y bar is this 8.029. All right. So if the mean is 8 and not bigger than 8, is 8.029 unusual? All right. So we calculate that probability. That's the p-value. So the p-value depends on the null being true. So when we come up with our test statistic, we use the mean from H0 to get my test statistic. All right, so here, all right, if I go back, all right, so we said Y bar, we just said was at 8.0, this is what actually occurred, 8.029 miles per hour. And the standard deviation of all those observations, this was 3.813 miles per hour. And then my sample size was 1,460. All right, so my test statistic here, this is going to be Y bar, which is 8.029, minus the mu from H0, go to H0, it's 8. That's what I'm trying to prove. I'm trying to prove it's bigger than 8. And then S is 3.813. And then I'm going to divide by 1,460. Okay, so, and that, so on the top we have that difference. So we're at 0.029, that's not how much higher than 8 my sample was. On the bottom, this is also called, this thing right here is called the standard error. All right, so it's my estimate of the standard deviation, just like we had in the for the confidence interval. And this value is 0.0998, and my t ends up being 0.291. Okay. So there is my test statistic. T equals 0.291. This is my test statistic, right? And that tells me how different this 0.29 is from this 8, from what I'm trying to prove that my sample is bigger than that. All right, so a t, we kind of talked about a t when we did the confidence interval. A t is a lot like a z. Right? It looks very much like the normal curve. It's just the tail's a little bit fatter, right? So it's very similar. So, you know, so 0.291, right? That's less than one, that's like a third of a standard error. That might be, let's say right here. So here's 0.291. Right? That's my t. This is a t distribution. And this guy has n-1 degrees of freedom. Here, that's 1,460 minus 1. So this is 1,459 degrees of freedom. That's a lot of degrees of freedom. All right. So the p-value is the probability of being at least as extreme as my data set if the null is true. So in my data, I have 8.029 miles per hour. So this p-value is the probability of having the average wind speed for the year be 8.029 miles per hour or more extreme in which direction? Well, this is a one sample or one-sided test. So in the direction of bigger. So what's the probability of being at least 8.029 miles per hour if the null hypothesis were true? All right. So we're looking for the probability of being bigger than this t, this test statistic. So this guy right here is my p-value. All right. We don't have a table. We have a t-table, but it only has 5 values per t, or per degrees of freedom. All right, here's my t-table. And you can see each row is a different degrees of freedom. So the t, unlike the normal, there's only one normal curve, one standard normal curve. For the t, the more degrees of freedom that you have, the closer it gets to being actually normal. So having a small degrees of freedom means my tails are fatter, right? But if I look for 1,459 degrees of freedom, they're not on here, right? But I do have 1,000. So that's the closest one. But if I look here, the only values of t I have these 1, 2, 3, 4, I have 5 values of t. And none of them are 0.291. All right, they're all different values. So I have to use StatCrunch to actually get the p-value. What we use the t-table for, we use this to come up with the t-stars when we were doing confidence intervals. So we would say, okay, the first column is for 80% confidence intervals, second for 90, etc. All right, so I'm going to have to use StatCrunch to get my p-value. All right, so how do I do that? Well, I'm going to run a t-stats, and I've taken one sample. And I don't have the actual data. I don't have the wind speed for every single day in a table. I have summary information. I have what the mean of it was, the standard deviation, and the sample size. So we're going to run that. All right. So here I'm going to put in my sample mean, which was 8.029. All right. The sample standard deviation, this was 3.813. And my sample size, which was 1,460. So this describes my sample. The average wind speed was 8.029 miles per hour, standard deviation 3.813 miles per hour, and we had 1,460 measurements. And I'm going to do a hypothesis test. So here I have to state, what are my hypotheses? Well, the null hypothesis, what we were trying to prove is that the mean wind speed is bigger than 8, right? So the null is that mu equals 8, and then I'm going to change this guy to greater than 8. And then I'm going to compute. And I get this. All right? Here's my sample mean. There's that standard error that we calculated that was in the denominator. Here's my degrees of freedom, which is just one less than the sample size. Here's my t, 0.291 with 3 decimal places. And here is my p-value, 0.3857. All right, and we got this, again, we got this from StatCrunch. And we did, I got this right here, p-stats, one sample with summary, and then I put in my summary information. I'll put on all this information over here. And I changed my hypotheses. Mu equals 8, mu greater than 8. And then I got this is my p-value. All right, so what's my conclusion? Oh, I didn't give myself enough room there, did I? Hold on. Okay. So my conclusion is based on this p-value. So with the conclusion of a test, I always ask ourselves, is the p-value less than the significance level of the test, which we call alpha, and it's usually 0.05. That's what, normally it's a 0.05 significance level. So is my p-value less than 0.05? 0.3857 is definitely not less than 0.05, all right? So my three conclusions are going to be three nots. The first knot is, well, it doesn't matter which order. The first one I'm going to mention is that we're going to fail to or do not reject the null hypothesis. So what does that mean to not reject? So what it means, if I go up, well, let me just restate my hypotheses again. We have H0, what's that, mu equals 8. And the alternate was that mu is greater than 8. Again, these were the two theories that we have. And when I do not reject H0, what it means is the mean wind speed could be equal to 8. In fact, it could be less than 8. All right, so we cannot reject that it's 8 and say it's bigger than 8. All right. The second one is this is not significant. All right, my sample, my 8.029 miles per hour sample mean is not significantly bigger than my null hypothesis mean. All right. And so the last one, and this is the one that we always write this one in context of the research question. And the research question is the average wind speed for this site bigger than 8? And because it's a no, we're going to have I don't have enough evidence of that. All right, so the data does not provide sufficient evidence that the average wind speed, it's about the average, is over 8 miles per hour. Here's my conclusion. Okay, so I got my three nots. Do not reject the null, not significant. The data does not provide enough evidence for the alternate. All right, so whatever you put does not provide sufficient evidence for, after that you write the alternate, that mu is greater than 8. Mu is the average wind speed at this site. Okay, question, do you install the wind turbine? We were only going to install it if the average wind speed was over 8. Now it could be. I mean, this is an inconclusive test. So the mean could be over 8. But it could be equal to 8 and it could be less than 8. All right. So basically, I'm going to say no. All right. Because we're not confident. We don't have strong evidence that it's over 8 miles per hour. And then let's just say that it's large enough to justify the investment. And so we could put it up, or possibly put it up, and it's not worth it. All right. Let's do another example. All right, this one I'm going to do, I'm going to use a data set. And we're going to talk about significance versus practical differences. All right. So here's our example. All right, this is actually, you can pull this up if you want. So if you want to pause this, you can go to StatCrunch. I'll show you how to do it. But basically, we have a guy. He has a trading strategy, and he wants to test if he's making money. So he has the daily rates from this strategy. Okay. So let's go. We're going to go to StatCrunch, and I'm going to load it for you. Okay, I'm going to exit out here. I'm going to do data, load, shared data sets. And it's a one sample T, and it's daily rates. I just put one sample T daily, that should pull it up. Maybe not. Maybe I have the system. All right, I wrote it down. Okay, let's see. Daily, oh, it's, okay. Daily rates is fine. All right, just copy this. Let's see. Daily rates, one sample T. There we go. Okay. So here's our daily rates. All right. Let me see. This is, I have data now. I have a column of quantities. It's a quantitative data. I can look at a graph of that. I can get summary statistics. I need to get a graph to check conditions anyway. So let's take a look at what this looks like. That guy, compute. There's my histogram. And you can see some of these are negative, some are positive, right? And so what we want to test is if he's going to make money with this strategy, right? So on the first day, he would have lost 0.42%. The next one, he would have lost 0.7%, and so on, all right? So we want to know, is he going to make money? All right, so this is going to be one of my hypotheses here. So I'm going to have a null hypothesis and an alternate hypothesis. So the null is going to be that mu equals some value, and whatever value this is called mu zero. This is my test value. And this one's going to be mu and then the same value, but here I'm going to put less than, greater than, or not equal to in here. All right, so if he makes money on average, let's go back to the data. So if he makes money, the average of all these quantities should be what? Bigger than what? All right, so it doesn't state exactly what I need to do. You have to kind of use some logic. So basically, if the average is positive, all right, the average is positive, he's going to make more money than he loses. If the average is negative, then he is going to lose money on average. So the alternate here, the making money, is that the average return is going to be greater than zero, and this is going to be the average return equals zero. Okay. So what are the conditions? I got two conditions. One is the independence, and I'm going to abbreviate independence or randomization condition. All right, so where do I get my data? That's what I got to ask yourself. And so this was actually 1 year of data. All right, so this was 365 days in a year. And so I have to ask myself, it's definitely not a random sample. I guess maybe he could have randomly selected data over the past several years and seen what his strategy would have been on those days, but he didn't. He said this is a year data, and so it's not a random sample. But I asked myself, are the day-to-day pluses and minuses, are they independent? Maybe, maybe not. So maybe, I don't know. So if yesterday went up so much, is that going to affect what happens today? In general, I would say no. So yesterday's plus or minus probably doesn't have a lot to do with today's, but it could, especially if there's a tendency if it's going up over time or it's going down over time. Maybe, so I'm not sure about that one. All right. Is it representative? So the year of data representative of all years. Maybe. That's a maybe too. Because what if we just had a really good year in general? That may not, so that may not be representative of different types of trends in the market. So maybe not here either. So we're kind of questionable about whether it meets the independence and randomization condition. All right. So what about the size condition? So the size condition, which by the way, the homework calls this the almost normal condition. We have to look at a histogram. All right, and so let's look, and while I'm here, I will get some summary statistics because I want to know, I want to know how many observations I have. So I'm gonna select N as the sample size, and I'm gonna use the control key to select the mean and the standard deviation, because those are the three things we need for a test. All right, so we have 360 data points. All right. So that's a large sample, and for a large sample, we meet the almost normal condition as long as the histogram is not extremely skewed and no extreme outliers, which this guy is unimodal, maybe slightly skewed right, but pretty much, actually it looks symmetric. So this looks almost normal to begin with. So this is unimodal symmetric maybe. So my histogram, which I actually provided for you, and actually it's the mean, that little green line is the mean. So this guy is unimodal symmetric. Which is great, which means really, if with this shape, I don't even need a large sample, but I have one, all right? So, so this is gonna meet the conditions for the size. Okay, so now we have met our conditions. Now we need to compute my test statistic and p-value. All right, so the test statistic, this is going to be a t, y bar minus mu0 over s over the square root of n. All right, and at this point, I was given a data set. I don't know what those values are, so I might as well, what I'm going to do is I'm going to run in StatCrunch, I'm going to run the t-stats, but I'm going to run it with data, and then it'll calculate this stuff for me. All right, let's run it. So we're going to do t-stats, one sample, but this time we have data. I'm going to pick my data. I have to pick my hypotheses. And the default here is 0, which is what we want, but we wanted to say it doesn't make money, is the mean bigger than 0. All right, so from here, now of course I have this stuff over here when I did this as well, but it tells me the sample mean, that's y bar, is 0.242. So, and the standard error, which is s over the square root of n, is 0.096. Degrees of freedom are 360 minus 1, 359. And then my t is 2.526. And my p-value is 0.006. And so here's my test statistic and my p-value. And I have that output saved there. So what does that mean? So what's my conclusion? All right, and again, I need to ask myself, is the p-value less than 0.05? This time, it is. way less. All right, so we've got a lot of evidence for the alternate. All right, so now I'm going to have 3 yeses. I'm going to reject the null. All right, so let's stay there. The null was that mu equals 0. The alternate was that mu is greater than 0. So I'm rejecting the null, which means I don't think the average is 0. The average return in percent is 0. All right. And we call this significant. All right. All right. And so my sample mean, this is, by the way, which is, and that 0.242, that's in percent. All right. So this 0.242% is significantly higher than 0. All right, so it's enough evidence that the mean is not 0. So it's so there's that. And then the last one is that we have sufficient evidence for the alternate. That the average return is positive, so we're going to make money. All right, so this is where we get to this practical significance versus statistical significance. All right, so I have significance. So I know that it's going to be positive. So the fact that it's significant, does that mean it's very positive? So does significant here mean that we're going to make a lot of money? Right? Well, how much are we going to make on average? It was 0.24% over the year. Is that a big deal? No. Well, that's not very much. I mean, you're going to make something, but that's not a huge amount. So the fact that it's significant, but this is significant, significantly higher than 0, but that doesn't mean it's a lot higher than 0. All right, so statistical significance means I have enough evidence to disprove the null. All right, so we know that it's not 0, but it doesn't necessarily tell us that it's very far away from 0. So just because it's statistically significant doesn't make it a big deal. All right, that's all I have for you today, and that should be enough for you guys to do your homework. And I hope you guys are doing good, and I'll talk to you another time.